Thanks for having us presenting. It is very interesting also for us. We will talk about integration of MVR heat pump systems in industrial thermal processes. And I guess I also should tell a little bit about myself. I've been working in EPCON for about a year, actually, working as a project team member within mostly MVR heat pump projects. And parallel to this, I also pursue my studies at the University of in Trondheim at NTNU. So the agenda for this short presentation will be to briefly explain our company profile before diving into the MVR heat pump technology, and then we'll present a few case studies and references before summing up why EPCON could be a potential technology partner for your projects. Okay, so EPCON supplies turnkey separation plants based on evaporation and distillation. And in 2010, we developed the standalone MVR heat pump. And most of our technology is based on the principle of mechanical vapor recompression, where we have experience all the way back to 1986, where we delivered the first MVR plants. And today we are 21 employees located in Trondheim. We have delivered over 150 plants since the beginning. And as you can see at the top right here, we are present in most parts of the world, actually. And we are in the latest year experiencing a high growth and a high interest with the MVR heat pump. So over to our products. We supply, of course, the MVR heat pump, which will be the main topic for today. And we also have different kind of evaporators, which differentiates in the capacity range and also the viscosity of the products. And it's important to underline here that we are a system integrator. So we do not have production ourselves, but we combine equipment from different pre-qualified sub-suppliers when we design our processes. So just to keep it simple, first, our MVR heat pump principle. The objective, of course, is to replace fossil fuels and reduce the total energy consumption for the customer. And by swapping out fossil fuels with electric power and waste heat recovery, we are able to drive the CO2 emissions down to 0% with a very low amount of waste heat. So the concept of our heat pump, you can say, simplified, is based on three main pillars, and we're doing process integration in a sustainable and flexible way. And by this we mean that we make case-to-case specific solutions, both for new installation, but also for retrofitting in existing plants. And we are using both water vapor and process vapor in direct systems for as the working medium, which is environmental friendly. And the flexibility part is maybe the most important thing for us, which has led to a development of three different configurations of the heat pump. We have the closed cycle, the direct system, and the indirect system, which we will show in an animation later. We also have an optional bottom cycle to ensure a wider operating range in the lower temperatures. And as I talked a little bit about, we choose well-proven equipment at a technical readiness level of 9 for the processes of our customers, and this is through our pre-qualified sub-suppliers. And typically, we also obtain a high COP potential in the range of 4 up to 20. And it's possible to to handle several processes in the same system with the supply and extraction of heat in different stages. So if you look at the value chain of EPCON, we often start with some basic assumptions to make sure that the process fits our scope of supply. And we stretch this all the way to after sales and services, so we ensure a long-term relationship with our customers. And just to give a short introduction to what we do, we can look at EPCON as a black box in this case. We extract typical sources, preferably at the temperature above 50 degrees from the client's process. This could typically be air, district heating, steam, or other fluids. And by upgrading the heat, we can deliver up to 100 megawatts of heat to typical sinks, which could be reboilers, steam grid, district heatings, and so on. And it's also important here to underline that the sources and sink could be a combination of several of these applications. So to show an animation of first a direct system, we extract process vapor, which could be alcohol vapors or other solvents. We extract these directly from a client's process, and by feeding it into the MVR equipment, we upgrade the temperature and pressure before delivering the heat back to the client. And as you can see in the top right here, there is a typical energy flow sheet for our processes. We extract a certain amount of heat out from the client's process, and by adding an amount of electrical energy, we are able to deliver heat back to the process at a higher temperature and pressure. And here we have the indirect system, where water vapor typically is evaporated by the process heat source from the client, and then the upgraded high pressure water vapor is fed back to client's process. And typical heat exchangers here could be both the plate and tubular heat exchangers, as well as falling film evaporators, reboilers, reactors, and so on. Last but not least, we have the closed circuit heat pump, where we evaporate water at the heat source side by client's heat source. And in the same way, the water vapor is fed into the MVR fan, upgraded to a higher pressure and temperature. And by condensing the water vapor, we transfer energy back to the client's process. And the water then runs through an expansion valve to reduce the pressure upstream of the evaporator, such that the medium is ready for a new evaporation. And to show a bit of our flexible MVR systems, in this case, we extract two different sources from client's process. Here we have a medium pressure vapor and a low pressure vapor, which is then connected, as you can see here, and then fed into another MVR fan. And when we have the medium pressure vapor, we split the stream into two branches, where one of them is going directly back to client's process, and the other one is upgraded to an even higher pressure before returning to the process. And this is done mainly to optimize the COP and to fit the client's need in the process. So, as I said, EPCON chooses technology from a range of sub-suppliers, and we want to ensure a reliable and robust operation in many years for our customers. So to ensure high availability, we recommend planned service intervals, one annual service in addition to a semi-annual inspection, which could be done while the plant is still running. And we typically have a lifespan of our system of 25 plus years, with an operating range between 60 to 100%. And this has also been a turndown of up to 40%. And it's possible with even higher turndown, but this we would typically reduce in some recirculation and a reduced COP. And at the left here, you can see the rotary compressors that we typically choose from, and they differentiate both in capacity and the maximum delta T, as well as footprint and the maximum supply temperatures. So we usually choose our equipment based on the client's need, of course, and to optimize the total process and system. In this slide, we have two diagrams. To the left here, we have the operating map of our heat pump, where we have the maximum delivered temperature to the sink, this red line here, versus the delivered heat in megawatts. So as you can see, we can deliver temperatures up to 200 degrees, and we are also able to deliver systems up and below this red line. So the way you could interpret this diagram is that if you need a temperature to the sink of 200 degrees, you would need a capacity of the system of 14 megawatts. And it's also important to underline here that this diagram stops at 25 megawatts, but that's not the limitation, and we could go even higher in the capacity, up to 100 megawatt, as I've said before. So to the right here, the obtainable COP is shown, and it's typically within these red lines. And EPCON is always targeting to optimize the client's process by both decreasing LMTD and the delta T's in the system, hence increase COP. And what we are basically doing is try to shift this curve to the right to get a better COP and a smaller lift of temperature. So to show you a little bit about the EPCON approach and the way we think, you can say that we often start out with a base case, and we want to optimize the total system of our customers. So by doing close discussions with our client, we are integrating our system, and we're also using the in-house calculation tools and design tools. So we here start at the COP of 4.1 with a payback time of 5 years. And by doing an optimization of the total system, we obtain a COP of 4.75 with a payback time of 4 years. And by doing another optimization to optimize the total system, we obtain a COP of 5.5 with a payback time of 3 years. And we're also able to cut down from 7 to 6 MVR fans. So this results in a COP increase from 4.1 till 5.5 and 2 years of reduced payback time. So moving on to the case studies. In this case, we have a 5-stage MVR heat pump with the water in a closed circuit system, where we utilize latent heat from the top vapor of 2 distillation columns. The water is then evaporated and flashed before feeding into the fans, and the upgraded water vapor is then delivered back to 2 reboilers. 40% of the energy goes to reboiler B, and the remaining 60% to reboiler A. And in this case, we obtain a COP of 8.2 with a total temperature lift of 45 degrees. The next case study is a direct MVR heat pump system where we use hot water from district heating as our energy source, which is directly flashed and fed into the compressor train at the different stages. And we also send the water vapor back to the client's process at 3 different stages, one at 110 degrees, 130 degrees, and 150 degrees. And in this case, we obtain a COP of 6 with a total saving of 12.5 megawatts. To show you some references, we have an indirect MVR heat pump system where the top vapor from the column 1 here is recovered in a heat exchanger, which in this case is a falling film evaporator. This evaporates water in an indirect system, which is then fed into a train of 4 compressors before being delivered to the bottom of column 2 is in this column train. So in this case, we obtain a COP of 7.7 with a temperature lift from 87 to 112 degrees. Here we have a little older reference from 2014. This is a closed MVR circuit, which in a way is quite similar to the other reference. Here we evaporate water by utilizing the top vapor latent heat from the column, and the water is then compressed to a higher temperature and pressure before being fed back to the reboiler. So in this case, we upgrade and compress water vapor from 75 up to 89 degrees C with a COP of 13. So to summarize this presentation, EPCON aims to supply efficient process integration where we have a strong focus on the client's need. And we use our experience from 35 years of using well-proven MVR technology to deliver flexible and sustainable plans. Okay, so that is what I have. Thank you for the attention, and I hope it was an interesting presentation as well.